All right, folks. Today we're talking about triangle midsegments and the midsegment theorem. So here we go. First off, a triangle midsegment is what you get if you've got a triangle and then you find the midpoint of two of the sides and then connect those midpoints. So actually each triangle has three possible midsegments. That's one of them. If you find the midpoint of the third side and then connect that, there's another, and then we can connect one more. So there we have it. Those are all three triangle midsegments. So with that, midsegments have a couple of interesting properties. Otherwise, we wouldn't be talking about them. And it's the midsegment theorem. So if you've got a midsegment, it is parallel to the third side and half as long as the third side. So what that looks like is, let's say we've got a triangle. Here's our midsegment. And then we draw the same picture because it's if you have the midsegment, then these things are true. Oops, there we go. Okay, so if you've got a midsegment, then the midsegment is parallel to the third side, to the side that's not involved. And then it's also half as long as that third side. So if this is some X amount of units long, then this third side is 2x. So if this is 5, then this is 10, and vice versa. If this is 36, then this is 18. If this is 2 million, this is 1 million. We get the idea, hopefully. So we can use these properties to do a couple different types of problems here. The first one is a little bit more conceptual. We've got, or at least it's, involves letters and not numbers. We've got this information that we want to label in our picture to start with. So I'm going to label QC is congruent to CS, QA is congruent to AR, and SB is congruent to BR. So that information is what tells us that these are all three midpoints. So these are the three midsegments for this particular triangle. So from there, we can complete statements like CB is parallel to what? Well, if we look at CB, this is the midsegment. The opposite side to CB would be QR. So that's the one that it's parallel to. So we can say CB is parallel to QR. So again, we could do something similar with CA. So here's CA. It's going to be parallel to the side that's opposite CA, which would be this one, SR. And this one, it's not asked, but for a little bit of extra notes credit, we could also do what is AB parallel to? Well, that would be QS. Got to round out the picture, right? Anyway, that's one kind of thing we could be asked. Another type of thing we could be asked is AB is congruent to what? There's two segments on here that AB is congruent to. So if you look at AB, that's the midsegment that's involved with this side QS. And C is the midpoint of QS. So that means that QC and CS are the same length and that AB is half the length of this whole thing. All that to say, AB is the same length as QC and CS. And hopefully that kind of visually makes sense as well. So it's the same length as QC and CS. So all three of these will be the same length. And we can do that with any of our midsegments. So like with QA here, it says that QA, we want to know what that's congruent to. Well, we know QA is congruent to AR because we already have that. But it's also congruent to CB, the midsegment for that side. And then, for extra notes credit, we could also round out our picture over here. AC is going to be congruent to SB and BR. So we can mark that one. And there we go. So that's one kind of problem that we might be doing. Another kind, if we jump a little bit more concretely into this with numbers, and look at this picture down here, we're told in the first one that Mn is 8 and that Lk is what we want to know. Well, if Mn is the midsegment, then Lk would be twice as long, according to our midsegment theorem. So 8 times 2, which would be 16. All right, then we can go the other way around. We could go from Lk to Mn. If Lk is 30, like in this case, then we'd have to go cut it in half, though, because Mn is going to be smaller. So we divide by 2, and we get 15 for Mn. All right, so we have this relationship that this one is twice as long as this one. So if that's the case, let's start bringing some algebra into this. If we have this expression 2k plus 3 for this side Mn, then 2k plus 3 here, well, I can do the same thing to get Lk as we've been doing before. Back here, we multiplied by 2 to get it. We can still just multiply by 2. Don't let the letters in there freak us out. 2 times 2k plus 3 is going to get us 4k plus 6, because we do have to distribute. So that's only the only common place of making a mistake here is forgetting to distribute to both. But Lk would be 4k plus 6. All right. So that's great, but we can't really solve for the missing variable, though, because we don't have any other information involved. But that should kind of move us forward into a problem like number 8, where we can solve for x. And so on this one, I'm going to actually write on the picture. It tells me that Mn is x and that Lk is 3x minus 2. And I want to find x, Mn, and Lk. So if that's the case, then we can go, well, we can't set them equal, right? That's the first thing that we should kind of be thinking about, right? A lot of times people go straight to, oh, I'm just going to set things equal. And we can't do that this time, unfortunately, as we should notice, even visually, that this is definitely much smaller than Lk. But we did just talk about how this one multiplied by 2 gets us to Lk. And that's exactly what I'm going to do here. I'm going to multiply this by 2 to get 2x. And that's going to be equal to 3x minus 2. And then we can solve for x. So minus 3x on both sides. That gets us negative 1x. And then this is a negative 2 over here. And then we divide by negative 1 on both sides, and we get x equals 2. All right, so that's part of our answer, x equals 2. And the nice thing is, since Mn equals x, Mn is also 2. Now we might ask ourselves, do we actually have to plug 2 back into Lk to figure out what it is? You certainly could. But you could also remember that if I take this and multiply it by 2, we get Lk. So Mn, if I multiply that by 2, we get that Lk is 4. Either way you want to do it is totally fine. All right. So that's another kind of problem that we might be asked to do. That's probably one of the harder of the types of problems that we'll be asked to do. So if that's as hard as it gets, that's not completely awful, right? Okay. So shifting gears just a little bit here to talk about what happens because of the lines being parallel to one another. So it introduces angle JMN down here. JMN, that's this angle. And to better see the parallel line angle relationship, I'm going to extend my lines just a little bit here and extend this transversal, because we know that these lines are parallel to one another. This acts as a transversal, and we want to know what angle is congruent to angle JMN in this picture. And it's actually that one, angle MLK. Why? Because their angle relationship is corresponding angles from back in chapter 3. So our reason, corresponding angles. All right. Well, if that's the case, then it can lead us to some problems like these, where we have angle JMN is 80, so that's this one here. And while we're at it, since we talked about these two being the same, I'm also going to label that this one's 80. And then it says angle J is 40. So that's that angle right there, 40. And we want to find angle JKL. That's that one, JKL. Okay. So now that we've got some stuff labeled here with this being 40 and these two being 80, if I take a look at the bigger overall triangle here again, and remember that the angles on a triangle add to 180, we can just go 180 minus 80 minus 40 to get my remaining angle in the triangle, which is 60. So then measure of angle JKL is 60 degrees. All right. So that's another kind of problem you may run into. Now I would encourage you for this next one. Well, first I would encourage you to redraw the triangle because we're supposed to use the same picture, but now ours is all cluttered. So I'm going to redraw JLK, MN, and then it says that NM is 3x minus 10, and that KL is 5x minus 2. Okay, so pause the video real quick and try this one on your own. See if you can find an equation that would help you to solve for x. Then go ahead and solve it and check back in to see if you got it right. And then I'll solve it here as well. All right, hopefully you paused the video and tried it. If not, or if you're not sure if you've got your answer correct, follow along. We'll see what we can do here. So on this one, it's the same kind of problem as number 8, where you had to multiply the MN part by 2 and set it equal to the KL part. So I'm going to do the same thing here. Multiply the midsegment part by 2. So 2 times 3x minus 10. And it's equal to the opposite side, the KL part, 5x minus 2. And then from there, it's just a matter of solving it. So we do the distributive property. We get 6x minus 20. And then I would subtract 5x from both sides so that we get just 1x minus 20 equals negative 2. Because remember, that is a negative that goes with it. And then add 20 to both sides. We get x equals 18. All right. So there's our answer. If you were asked to go back and find MN and LK like we were up here, make sure that you plug it back into the original one, not the one that's been multiplied by 2. If you do that, you'll just end up with the length of LK instead. But anyway, there we have it. On the next page, we're going to talk a little bit about what happens in the coordinate plane with these. So let's go ahead and turn the page. Okay. So if we look at these in the coordinate plane, you can show that the two lines are parallel to one another, that the midsegment is parallel to the opposite side. And you can also show that this length is half of the length of the opposite side. And there's a couple different ways to do this. So the first thing we want to talk about here is slope, because when you talk parallel lines, it always helps to talk slope. So to show that MN is parallel to RS, we're going to find the slope. Because if you remember about parallel lines, they have the same slope. Perpendicular has the negative reciprocal slope. Parallel has the same slope. So that's where we're headed with this. And with slope, just kind of jog our memories here. Usually lowercase m is the letter we use for slope. And the slope formula, you can use coordinates and go y2 minus y1 over x2 minus x1. You might have also heard of this as change in y over change in x, or as rise over run. And rise over run is the one we're going to emphasize a little bit more today, because we have a nice graph here that's easy to read and easy to count on. We're not counting, our points aren't 26 units apart. They're pretty close together. So with that, I'm going to start by finding the slope of mn. So to find the slope from here to here, I count how many do I go up? 2. That's my rise. How many do I go over? Also 2. That's my run. So my rise over run here is 2 over 2. And 2 divided by 2 is 1. Then we're going to do the same thing, but for RS. For RS, to go from here to here, we go up 1, 2, 3, 4 for our rise, and over 1, 2, 3, 4 for our run. So 4 over 4 for the rise over run, which also reduces to 1. So now we should notice that this is the same slope. Hooray. That's enough to show that those two lines are parallel to each other. So we're good to go there. Now, if I was asked to show that mn is half the length of RS, there's a couple different things we could do. We could use the distance formula if we want to. You could find your coordinates of all of these things and go, okay, distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And you could find the distance from n to m and from s to r and figure out that one of them is half the length of the other. Another thing you could do, though, if you did not need the exact length, like if you weren't asked for the length of mn or asked for the length of sr, there is something else you could do instead that involves the rise and run. You could figure out some rise and run ratios. And so what I mean by that is for mn, we said that the rise was 2 and the run was 2. For RS, we said that the rise was 4 and the run was 4. Notice the relationship here between the rise and the rise, 2 over 4, which is 1/2. And between the run and the run, also 2 over 4, which is 1/2. If you get 1/2 for the rise ratio and the run ratio, both of them, that would indicate that this one, that mn is half the length of RS here. So that's another way that you can show it without actually having to find the length. But you could also find the length of both using the distance formula. I'm going to cross out that part of the notes and jump down to the last thing here. And on the last one, we're going to do the exact same thing that we did up top. But instead, I would encourage you to pause the video and try this one on your own. Find the slope of both the midsegment ED and of the opposite side BC. And then show that their rise and run ratios have that 1/2 relationship. Then unpause the video and we'll do it together. All right, so hopefully you paused it. Here we go. Here's how we would do it. So to show the same slopes, the slope of ED, the rise over run here from E to D, you have to go down 3. So our rise is -3 over 1. So the run is 1. Reducing this, we get -3. For BC, I have to go down 6 over 2. So negative 6 over 2, which also is negative 3. So we've got our same slopes going on. Then, identifying those rise-run ratios, ED, the rise was negative 3, the run was 1. And then for BC, the rise was negative 6, and the run was 2. So same thing there. We are figuring out that negative 6 or negative 3 over negative 6, which is 1/2. And then the 1 over 2, which is also 1/2. So we both have that 1/2 ratio. And that's it for midsegments. Hopefully this was helpful. If you have questions, let me know. Otherwise, have a great day.